Hello? Bon, okay. So I am the last speaker. There must be one. It's not a problem. The problem that I have a tight schedule and I probably have to leave at 1. So I apologize in advance if I leave you in the middle of nowhere or in the middle of a question. But don't worry, my co-author is there. Okay, so I skip the title, but nobody is interested in the title. Which one? Suite droite. Droite là, l'autre droite. Ah. Bah, tant mieux. Hein. Okay, so I will go directly into this place because it's gonna work. Ah, good. Okay, let's try to have some fun. Okay, it's working. Okay, so very quickly, what happens when you want to make a query on Google? I make this query, who built Stonehenge? This is a serious question, by the way, so it's not funny. You will be punished for that. And you see that answers are ranked. And are ranked between the popular pages and the least popular pages. It is not a guy of Google every time you receive a query, he says, oh, this answer seems reasonable, and the answers there are not reasonable, so they are less popular. No. There is an analysis of the popularity of the web pages, which is done by something called the web crawl, the Google web crawling. The Google web crawling consists to make a random walk between the pages. You take in one page, you take a randomly pointer in this page, and you go to another page, and then you walk, and basically the stationary weight of this process, this random process, the stationary weight of the node is the popularity of the page. Because you can have a page which has many pointers coming to it, but the pointer may come from very unpopular pages. Therefore, the definition of popularity has to be extended to consider the topology of the graph around each node. Therefore, there is a random walk can be factorized as a deep search, deep first search, DFS. So this is just to explain why it is interesting to study the DFS. Of course, the DFS is not a really brand new topic, but there is an excuse. Okay, here we are going to look at a random digraph. What is important that okay, so there's already a mistake. It's a directed graph, not undirected. There has been work on undirected graph, but the graph of the web is strongly undirected. Because if you point to a page of journal, does that mean that the journal will point to you? Fortunately, that's life. Okay, so it's a very directed graph. So every vertex select in this model eta outgoing neighbor arc, and you have the probability distribution of eta. So eta is out degree. Is the correct out degree. In this case, it's possible that a vertex can loop on itself. If you want to be popular for yourself, you just loop on your own. Also, a vertex, a web page can point to the same other page, but by several pointers. It happens very frequently. Apparently in textbook. Textbook, you see in this page the solution of the exercise. Therefore, but when the average degree of the average degree is greater than 1, the deep search starts on a supercritical tree. A supercritical tree means that it may develop in a giant tree. Some selected reference of course. We put our reference in the very fundamental references. Doesn't hurt. So
You sure about bullet one?
for what?
For targeting DFS. Sounds like a gameplay.
You ask Google and you will tell Targent. Targent. Oh, okay. Okay, I can put that. Who invented this? Who is the person who invented this? No, we just yelled. So, okay. I don't care. Okay, other question? Donald Knuth asked us to solve one exercise on his fourth volume, number C or number D, so something which has already 1,000 pages, the exercise. And there is also the same exercise we did, but an undirected graph, which is not the same. And here was the presentation of last year. Good. What happens when you do a deep first search on a supercritical situation? So what happened? You have first a giant tree. The giant tree has first ascending phase. It means that your search is deeper and deeper and deeper. Then at some moment, the number of visited nodes is such that basically the remaining out degree of each node is in average smaller than 1. So in this case, you are in the descending phase, and at the end, you finish your descent with small trees. In fact, if we do magnification at the very beginning, you have a lot of very small trees. In fact, it's the first supercritical tree. There are a finite number before you get into supercritical ascension. This is like a C-plane. You know what is a C-plane? It bounces on the waves in the very beginning, and then take off. Then it do its fly, and then coming back, it lands, bounce on wave, and go back in the harbor. So all these bonds won't be omitted in the analysis because it'll be inside the error bound. So it is C-plane, no? Hydravion. No, have to be translated in fact. So this is a pseudocode of the deep first search. This is a classic pseudocode. I will always look at this pseudocode, but in fact, there's two versions of this code, which are not, it is hidden. There is a linear implementation. In the implementation, you have for each vertex in the neighbor, there you store all the arcs of the neighborhood. This is a linear. This is what you did when you were young, when the recursion was not invented. I'm talking for Bruno. So it is a linear implementation. The whole neighborhood is stored. So in this case, with the size of the memory, we call it the stack index. The stack index counts all the arcs you have stored since the beginning, knowing that every time you proceed to arcs, you move these arcs in the memory. You don't need to take care of it. And you store all the incoming, the outcoming arc from this new visited node. So theorem 1, basically, we have an exact expression of the distribution of the stack size with an error of square root of n. So it is a central limit theorem. And it has a closed formula. So we are very happy. So we have closed formula. The proof is very easy. So I'm not going to talk about the proof because it's very easy. So basically, when we say we are not going to talk about something, the speaker always talk about this. So, okay, so it is the stack index is just only a Markov chain. What you do when to discover the next node, you have basically to add the neighborhood, the arcs towards the neighbor of the current visited node, to remove one because you have removed this node. And you have a collection of arcs, but this collection of arcs, some have been probably been visited already. So you have to remove all the visited node arcs before. It's on the number of arcs you have to remove. It's just a geometric distribution, and it will, you can easily find the distribution of this Markov chain. It's martingale, just everything, every kind of mold. There's nothing special here. There was a nice remark, but nobody cares. Okay. Now, the hard part of the talk, that I will skip probably also. The hard part is, I still have time. If you have still memory, some memory, it is the same pseudocode, but there is a difference now that I'm taking the recursive implementation. Only one neighbor is stored. The other neighborhood is, the rest of the node is not stored, because when you will go back to this node, you will continue the exploration of the neighborhood. So there's no need to store the neighborhood, the current neighborhood. So it is a recursive implementation. The complexity of this, the memory complexity of the recursive implementation is different than the complexity of the linear implementation. And this is basically the aim of this talk. It is the depth of the search is all the arc you have stored since the beginning. It is basically the memory you are occupying, the stack is occupying during the process of visiting the nodes. So there's a theorem which is look like the previous theorem. There is an expression. The expression is not as simple as we may imagine. It is using the survivability, the probability of survival in a supercritical tree. And so it is when it is in the ascending phase. In the descending phase, the survival probability is it's always to mix is 0 or 1, forget always, basically is trivial. Therefore, you cannot use this formula. In fact, it is the depth is equal to the mirror of the depth on the other side of the, I will show you what is the mirror. And this function L of theta is 0 when theta is greater than theta 1, basically when the tree come back to 0. Here, you probably have noticed, so when the speaker said that you have probably noticed, he's sure 100% you didn't, but so you have noticed that the error, with a lot of fight on this, the error is not square root of n, it's n minus epsilon. And the current value of epsilon, we are not sure that it may change, still change the future, is 1/5. It may change again. It was 3 days before the deadline, the hard deadline. The value was changing every day.
Going down.
It was going down, of course. So the mirror function, basically, when you are up, you go down, up.
I asked the question the right way around.
You lost your right to ask question afterward. Up.
You can't
Up.
switch the organizer.
I can choose not to answer. What I was saying, okay, let me check. Okay. The mirror function. Now, the mirror function is basically what is the proportion of already visited node which correspond to the depth in the descending phase, which correspond to the depth in the ascending phase. We call it the mirror function. Yes, it's Lambert. Yes, it's Lambert W. And what you notice immediately is that it depends only on the average out degree. The function L of t of the slide before was depending on the function, as a generating function, the distribution of degree, but that depends only on the average. And here is for lambda average degree 2, it is the plot of this function. It has a closed form, so there is nothing special. Here, yes, it is explained that it's a survivability probability in bien-aimé Galton, Watson, tree. So to remember the three guys. This is as everybody here knows. So when we say that, it means that not everybody. I am the one who doesn't know. It is a non-trivial solution of this fixed point equation. Therefore, the function L of theta, unfortunately, doesn't have a nice closed formula. It has for some cases, for example, when the degree is constant, we can find a closed formula that I'm not going to show because they are horrible. But there's no universal simple expression, contrary to the stack index. Or the proof is not easy, so I can stop here. So basically, but I won't going to stop here because when we say we stop here, but no, you won't stop here. So basically, the ascending phase, you notice that you are in supercritical situation. So sometimes you meet a node which is the root of an infinite tree. Something will be infinite if you don't change the number, the ratio of already visited tree. So you want to know, you call it a ladder vertex because it is the root of an infinite tree. One of its neighbor is a root also an infinite tree. It's the second ladder vertex. It means that when you meet a ladder vertex, it means you are not going to come back during the ascending phase. And the depth increase one by one with some bump here. There are some bump because you explore some neighbor which produce a finite tree before you get to the supercritical tree. The degrees of the visited tree are independent. They are independent of the past, of what happened before. If you know only the number of already visited nodes before, the distribution of the visited nodes after is independent. And when you are descending, you have the same independency, but this is not with respect to the past, but with respect to the future. It's simple. And the starting phase, what happened? You come back to your ladder vertex. You have to explore the remaining degree. And then you get down, explore remaining degree, get down, get down. So with that, you can describe how many how many steps you must do before incrementing your depth, on how many steps you must perform before decrementing your depth. This will give you the distribution you are looking for. Of course, it's always complicated because it's always complicated. It's life. So in the ascending phase, the average number of visited vertex is this quantity. On the descending phase, it is a little harder because you have to consider the remaining degree. So you have to remember, I was on this vertex. I explore that many of the neighbor before, so I have to visit the remaining. So before it was easy because we have a geometric distribution. Here we have the general distribution. We need to keep track of the remaining degree. He has this, nobody cares. It is the formula of the number of vertex to be visited before dropping because there is a remaining degree on the side. Nobody interested. This is the end. No, it's not. It was just to check if you were following. This was not the end. No, it would be far too easy. No, this is it is the function L of theta, I of theta, and so it is the profile of the depth on the stack index. So for linear and recursive, I mean, we see that for the case when the degree is deterministic, is 2, we see that something strange happened. The linear implementation has take less memory than the recursive implementation. You are not allowed even to upload. And so it looks strange, but in fact it is not that strange because in the recursive you add 1 every time you go to the next neighbor. Here you add 1 only in the case you didn't exhaust the neighborhood. Therefore, it is the reason why it is below. But when you consider a deterministic number of neighbor, 8 for this case, life becomes to be normal. That basically the linear implementation is really more memory consuming than the recursive implementation. And that's what you expect with the web. The graph of the web has a lot of large degree. And that's all. That's all. Yes, okay, you're alone. Start you.
You can be. No, you wouldn't. So, questions? Or Philippe or something?
Could you tell me a bit more? Like, I didn't really understand what methods did you use? Like, is it generating? Did you do like generating functions things or probabilistic things? What did you use? Martingale?
The martingale specialist is there.
Then, but did you use martingales or did you? I'm just asking what
for the first
for the ascending phase.
The stack index is so clean the Markov chain.
Yeah.
Markov with, of course, the parameter changing, so non-homogeneous Markov chain. And then there's enough result in.
So that's for the ascending phase? No.
No, this is for the linear implementation.
For the linear, okay.
Yes, this is always the same program we analyze, but
Okay.
one is linear,
yeah,
and the other is recursive.
Okay.
But it is the same. And the hardest
recursive.
is the recursive.
And so for this one, like it looked like you had almost explicit calculations with like.
Yes, we have to take into account the number of the degrees, the remaining degree,
And so then was it generating function?
and we use using function, but you could use something else, I guess.
no.
That's not
Cool.
not an issue.
Great.
More questions? Any other questions? No? Oh,
Out of curiosity, do you have results on the large deviation on the curve? What's the error term? What is the error term on the deviation on the curve in a typical execution?
It will be maybe. We have for the stack index, we have large deviation, everything, because it's almost
Yes, it's
from
the
textbook,
Gauss-Motion tree.
but
Yes,
here no, it's really it was difficult to get epsilon larger than 0. So I do not have yet large deviation, but we expect. Sorry.
It's not for large deviation, but typical deviation.
Yeah.
Probability of the deviation.
Yes.
Think about large deviation with very small probability.
Okay. Okay.
Don't think so. Not yet.
Okay.
Yes, probably we will. Ah,
Okay. Thank you.
this time.
Yes, I have perhaps the same train as you. So just to comment on what Sebastian said, that he was skeptic that Tarjan was really the father of
Oh,
this.
good, good.
So there is some old work by Edouard Lucas, in which way to escape a maze, and this is the DFS. So 1 century ago, more than 1 century ago, and Lucas is saying that it is from a letter who got by Tremo. So the Tremo algorithm is the ancestor of this.
Yes. Yes. This for you.
well, thanks to all the speakers. Thanks to everyone that stayed until the very last moment. I think we have a packed lunch, and it's the time for the organizers to say something. To close the. Yes.
Thanks a lot to all of you for coming and for staying until the very end. And also thanks to all the speakers, because the conference is a success thanks to you more than thanks to us, I think. So have a nice trip back, and see you soon, I hope. Bye.
And thanks to Cecile for doing the very hard work on the local part, where there's much more that can go wrong, but nothing really went wrong. So cheers.